if you want to do that. So we're going to start today. Our first speaker is going to be Mario, who's going to be talking about HTR.
Good morning, everyone. Thanks, Elliot, for the introduction. So as Elliot mentioned, today I'm going to give this talk about HTR, which is a compressible Navier-Stokes solver, and that I've been developing since 2019. And the content of this talk is basically going to be divided in three sections. The first part is basically about what is HTR and what are its applications. Then I'm going to discuss about a few of the solutions we implemented to leverage Legion to achieve performance with HTR. And at the end, I'm going to tell you something about how the HTR project is evolving and what is the future of HTR. So in a few words, HTR is a compressible multi-component Navier-Stokes solver that is able to consider finite rate chemistry which is computed at runtime. It is formulated to handle curvilinear multi-block computational grids, so it can consider relatively complicated geometries, and is currently compatible with NVIDIA and AMD GPUs. And it has been natively implemented to use Legion. Now, as the name of the solver may suggest, this is the main intent of when HTR was developed was to create a solver that was capable of solving hypersonic flows. And in fact, its main application is actually the solution hypersonic high enthalpy boundary layers, whereby the high energy that is developed within the boundary layer triggers complex thermochemical phenomena such as vibrational non-equilibrium, dissociation chemistry, or vibrational non-equilibrium, which coupled with the transport phenomena of fluid dynamics to give relatively complicated physics. However, the HTR solver over the years has been extended to consider several other applications. For instance, we are using it to simulate and to analyze rocket burn ignition in the PISA project. I'm going to tell you more about it in the next few slides. Or, for instance, to study shockwave turbulence interaction in hypersonic and compressible flows in general, or combustion, and specifically electrified combustion, whereby an external electric field is applied to a flame to change its behavior and to stabilize it. Now, in the next few slides, I'm going to give you a few examples of projects that use HTR and actually support most of the developments of HTR that can give you an idea of what are the applications, give a better idea of what are the applications of HTR. The first one I want to mention is the Insieme project, which is funded by the Department of Energy through the PISA-3 program, and is based at Stanford with the collaboration of University of Colorado and University of Purdue. And the main goal of this project is to predict probability maps for laser-induced ignition of a simplified rocket burner. As you can imagine, this project is quite complicated, and the idea is that basically we want to predict how reliably a laser can ignite cryogenic propellants in a simplified rocket burner. In order to do that, HTR had to be extended in order to consider two-phase flows coupled with compressible phenomena, turbulence, mixing of different species, ionization due to laser, and sustained combustion if we are able to ignite these the propellants that are present within the burner. And on top of that, since we want to predict probability maps, we also have to perform order hundreds or even thousands of calculations in order to analyze the entire phase space of the uncertain parameters that govern these. this phenomenon. Another project that started recently and that uses HTR is the Iceberg project that is funded by the European Office of Aerospace Research and Development of the Air Force Office of Scientific Research. And this project has the objective of assessing how self-similar is the distribution of chemical species within the hypersonic boundary layers. And particularly, the idea is to see if using different scaling laws, we are able to collapse all the chemical species profiles that we can compute within these boundary layers. And in case we're able to do that, to devise reduced order models for these distributions. In this case, HTR is utilized to produce all the direct numerical simulations that are necessary to evaluate the subsimilarity of the boundary layers. Another example is this other project, which is funded by the European Union through the Ministry of University of the Italian Ministry of University, which has the objective of devising a conceptual design tool for suborbital vehicles. Now, you probably know that designing these vehicles involves several disciplines which are coupled. For instance, something that predicts the size and weight of vehicles, something that optimizes its trajectory, and something that computes what is the loads, the aerodynamic and thermal loads that are generated by the flow around the vehicle. All these disciplines are coupled together and are utilized to predict to perform this conceptual design exercise. And the HTR solver in this case is used to perform direct numerical simulations of several elements of the vehicle and to predict the thermal and mechanical loads on these elements. These data are then fed into some kind of reduced order model, something similar to what you see on the bottom right of the slide, and these are then go back into the conceptual design process. Now, these are just 3 examples of the applications of HTR, and clearly, if you are interested in some of these, or you, I mean, just feel free to reach out. I can give you more details even in the questions afterwards. Now, let's switch gears to the second part of the talk, which is more about how we use Legion to achieve performance. And in order to do that, so I thought that it's a good idea to actually use a case study that can be useful to explain some of these features. And particularly, I'm gonna use the a case study that is similar to the PSAP-3 burner to the rocket burner that we are using in the PSAP-3 project. Now, this burner has quite complex geometry and has a lot of physics that happens within it. Therefore, there are billions of degrees of freedom that are necessary to describe the flow within this burner. And from a computational standpoint, it's quite challenging to have accurate predictions of the flow within this burner. If we focus on the geometry of the burner, we need to discretize it using a structure in the space which is composed of multiple blocks. And these blocks are connected in a way that is non-trivial in order to describe the entire topology of the burner. Now, what HTR does is actually to partition this complex index space and execute several tasks that have different stencil access and update the solution of the flow within the burner. Now, if we focus on one section of this PSAP burner, it looks more or less like this, like a cross. And we need to keep in mind that to preserve the topology of the geometry that we want to describe, some of the faces of this cross are connected to each other. Now, the main thing that we do with HTR is actually to partition this domain into several pieces. And each of these pieces, as I mentioned before, we solve a set of conservation equations, which more or less look like what you see on the bottom left of the slide. So we have a left-hand side, which is a time derivative, and then a series of terms on the right-hand side. Now, each of these terms is computed by a separate task. And to correctly compute these terms, we need different data, mainly to support different stencils that we apply to for each of these terms. And depending on how the domain has been partitioned and how the tasks are mapped, some of these data can be locally available on the node, or may not be, or may need to be communicated across nodes or different elements of the HPC that we are using. Now, the dynamic scheduling that Legion performs of the task is actually helping a lot in achieving performance with this kind of problem, because we actually can easily apply an atomic coherence model across all the tasks that assemble the right-hand side of the conservation equation, allowing Legion to shuffle this task and perform the operations that have the data ready before other tasks that maybe need to wait for communications. And this helps significantly in hiding communication overheads. Clearly, performing something like this with a different in a different system may require significant effort, right? While with Legion is actually quite simple. Another example I want to give you is actually something connected to a feature of Legion that has been implemented relatively recently, and it's distance padding. So one of the problems that we have is actually that we need to compute these stencil operations across this domain that, as I mentioned, different interconnections. So for instance, let's say that we want to compute a certain task which has stencil access on the grid subregion of the domain. And this green subregion, to support these stencils, needs the data in the red blocks that are positioned in two different regions of the cross. So the old implementation that we used to have was based on a fine accessor, which are actually very fast in accessing the data in the memory. However, I have some problems connected to this specific configuration. So in particular, as you see, the bounding block of the indexes that might be accessed by the task can be quite larger than what we need, particularly if we compare it to the green block, which means that Legion, or in general, one could allocate a lot of memory. And moreover, during the execution of the task, the computation would be quite inefficient because you will get a lot of random accesses in memory. And also, every time you are in the green task and you want to do a stencil operation, you need to check whether you're going to access something in the red block, which is maybe located somewhere else and need a transformation of the indices, or you can just do a simple offset of the indices. Now, thanks to the implementation of the instance padding, we were able to significantly simplify the implementation of our tasks. And particularly, we did it by accessing the green subregion using an affine accessor, whereby we are putting a padding constraint on the green task, and accessing the red subregions using multi-affine accessors. Now, specifically, what we do is actually to ask the runtime to allocate some scratch space on the sides of the green block. And before executing any of the kernels that we do in our solver, we first assemble the data into a single instance. And at this point, we have all the data laid out exactly how we need them, and we can perform our kernels by doing simple stencil operations and having good affinity of memory accesses, because we have actually laid out all the data exactly the way we want it. This actually gave us a significant improvement of performance, and actually, if you have something similar, I would recommend using something using a similar approach. Now, let's enter in the final part of the talk, which is about more the future of HTR and what's going on in this project. So, in order to understand what's going on, I think that it's useful to have a brief description of the history of HTR. So, mainly, as I said, the HTR development started in 2019, when HTR was fully implemented in Regent, was auto-parallelized, and could consider at most 5 species and a handful of reactions. So it was good enough for hypersonic flows, but definitely not for combustion, for instance. And I have to say at this stage that actually having the first implementation of HTR in Regent was actually particularly useful for us, because at that time we were not particularly familiar with all the constructs of Legion and all the interfaces that it has. And starting with Regent really gave us the chance of implementing this, of having a solver that worked in a few months with no prior experience on task-based programming. So I would like, if someone is starting using Legion, I would really recommend starting from Regent. However, as the number of applications of HTR grew, the number, we had to generalize the solver and to include more features. And as the solver was growing, its compile time were also growing, and we started doing some changes. Particularly in 2020, we started changing the parallelization strategy to a manually parallelized implementation, and porting some of the tasks to the C++ API to improve the efficiency of some kernels. In 2021, we had to start doing some combustion calculations. Therefore, it was necessary to also port chemistry tasks to the C++ API. And at that point, we were able to actually significantly increase the number of species and reactions that we were able to take into account. Actually, at that time we tested the solver for up to 40 species and 1,000 reactions, which is relatively good amount of detail for combustion if we are considering light fuels. And in 2022, we ended up basically writing most of the leaf tasks in the C++ API when we started implementing the curvilinear coordinates formulation, which significantly increased the range of geometrical configurations that HTR can handle. Now, as you can see through this brief story, the trend in the HTR implementation has been that we started from Regent, and then we increasingly moved to the C++ API of Legion. And like after 2022, we realized that basically we had most of the code implemented in C++ with a few tasks in Regent. And that actually having the two elements in the same solver with was basically creating more difficulties in the interface than simplifying actually our development process. Therefore, today we're actually moving HTR to a new version, which is called HTR++, which is entirely ported to the C++ API. And what I'm going to do in the next few minutes is actually give you a description of some of the solutions that we are using to actually make this porting. The first thing I want to discuss is actually the and this what we call the Legion interface. And this is a module of HTR++ that starts from actually two observations. The first one is that HTR and particularly HTR++ only require a small subset of Legion runtime objects and execution options. And the second observation is actually that is also that most of HTR developers are people like me who have a background more in fluid dynamics than in computer science. Therefore, it's actually beneficial for us to have something that simplifies, that slightly simplifies the interface with Legion, and that somehow streamlines the few operations that we always do, even if we lose some generalities with respect to the standard API. In order to do that, we basically implemented a number of helper objects that basically are in the middle between the application and Legion, and that performs several standard operations that we do throughout the solver. For instance, we have this manager that creates the field space and registers all the fields that we want to compute, that we want to add to a region, for instance. This has the advantage that basically it takes care automatically of destroying the field space, and basically simplifies the number of operations that at least a new developer has to do. And also has the advantage that as a byproduct, has the advantage that in the future, if we want to, for instance, for benchmark purposes, to have a version of HTR that doesn't depend on Legion and maybe has more limited kind of applicability, or has very limited type of execution modes, we can still do it by doing a different implementation of these objects that are between HTR and Legion. Another feature that that maybe it's worth that probably is worth discussing is actually the portability layer. So one of the things that we really liked about Regent was its ability of compiling the same source code in different kernels. And we wanted to have something similar in HTR++. For this reason, we implemented this portability layer, which is basically a set of template functions like this one for each point that takes a lambda and performs either a standard for loop or an OpenMP parallelized loop or a CUDA kernel or a heap kernel, for instance, depending on what is the value of the template parameter implementation type. And this is actually quite useful for us because we can implement the functionality of the code in a single place, in a single file, and significantly simplifying also the approach for new developers who maybe are not familiar either with CUDA or HIP, for instance. So the key features of this portability layer are that all sources, again, are implemented in the same place, and therefore it's easy to test and manage the entire source files. Again, new developers who are most of the developers of HTR are only familiar with C++, have a easier life if they want to implement something quickly. We can easily port the code to different architectures by simply specifying a new specializing this template function to produce a different type of kernel. And we also take care automatically of things like GPU reductions or other common patterns that we have in HTR while preserving, for instance, the deferred execution. And again, since this is something that we implemented but it's not mandatory, experienced developers can actually implement their own OpenMP, CUDA, and HIP loops within the task for debugging, performance, or other purposes. One of the other things that we are considering is actually the automapper. And this this work that has been carried out within the PSAP Center starts from the observation that actually the HTR has a significantly complex task graph that might have up to, I mean, a significant number of, that has a significant number of mapping decisions that are made. And the current mapper is something derived by default mapper. And it's based on experience, measurements, and what we believe is the best algorithm, but it doesn't mean that it's actually the optimal one. Therefore, within the PSAP Center, we have actually tested the automapper for the HTR solver, and we have seen that particularly in cases where the number, in configurations where we had larger number of nodes, therefore larger number of decisions that could be made, the automapper could actually improve the runtime of the solver significantly, considering that sometimes these runs are executed for days, if not months. So I guess I reached the end of my talk, and these are the conclusions. So if you are, if HTR is a compression Navier-Stokes solver that has been implemented in Legion and built to leverage the task-based constructs available in Legion. We are right now rewriting it in using the C++ API and evaluating the options given by the automapper of Legion to optimize its performance. And if you are interested in any of the things I've said, then or you want just to get involved in HTR, please reach out. And if I would like to thank you for your attention, and if you have questions, I'll be happy to take them.